All right, so we're going to go back and look at some of these elements and how they're organized on this thing called the periodic table. Elements, remember, are large collections of atoms of the same type, all have the same atomic number, meaning, that's not, I said that last time, it's not a true statement. They all have some atomic number. The atomic number is referencing something, but we can't break it down further than its individual atoms and still maintain its identity. We know that there's subatomic particles that are there, are protons, neutrons, and electrons, and we can get a lot of this information from looking at the periodic table. I think at the end of the module I blew this, or I printed this off for you. So you may want to, as we're going through this, pull that out and have it referenced. Did I do that?
Yes.
Okay, good. But this is one of many examples that you can end up finding online. This one's actually nice because if you look at the right-hand corner, upper right corner, right in here, it has the number of electrons in each of the shells, so that'll come in handy. Of course, you have to have perfect vision to be able to read it, because or a magnifying glass. I don't know. So let's talk about how this thing is organized. First of all, the atomic numbers run from low to high, left to right, and as they go down. So here I have 1 is hydrogen, 2, 3 through 10, 11 through 18, 19 through 36, and so on and so forth. So numbers get higher as they go left to right and get higher as they go top to bottom. And it's, as we know, the atomic numbers are determined by or state the number of protons that are present, and therefore the number of electrons also. So if I were to look at oxygen, oxygen is atomic number 8 protons, 8 neutrons, and its atomic mass is 16, so that must mean they must have 8 neutrons in addition. Periodic law states that when elements are arranged in order of increasing atomic numbers, elements with similar properties occur at periodic, i.e. regular, reoccurring intervals, and that's probably why they call it the periodic table. There is a method to this madness. We'll talk about the different, what is specific about the rows and what is specific about the columns. Two other ways that you can approach this is grouping of the elements or defining them based upon the classes. Grouping has to do with having similar chemical properties. And what determines the chemical property? The number of electrons you have, specifically the number of valence electrons. I'll get to what that is in a bit. Classes, on the other hand, have to do with similar physical properties, and the physical properties are determined by the neutrons, as we just saw. But first, let me talk a little bit about electrons. We know they're small, very minimal mass, negatively charged. They surround the nucleus in a cloud and are constantly moving. They stay in this orbit or shell that they're in. When they jump shells is when you actually have some some chemical activity going on. If you think of it as an onion skin, that layer goes on top of each other as the electron number gets larger and larger. The specific arrangement of electrons into the various shells are called configuration. There's up to 7 shells into which electrons can fit. The order by which their load is fixed, and this gives us the periodicity of the table. The total amount of electrons possible is dictated by the capacity of the shell. And if I take 2 times n, where n is the number of shells, and you square the n, that'll tell you how many maximum electrons can fit into that shell. Anytime they move with, I said, they involve some kind of energy being applied. as might not be apparent, but the more shells you have, the further you're getting from the nucleus. More shells, more electrons, and further away it is. The key one I want you to remember is that last bullet point, because that's the ones that we're going to be focusing on. The valence electrons, they're the electrons that are present in the outermost shell. And they have the highest energy, which means that they're the ones who are going to be reacting when two elements join up. To make matters worse, all shells contain subshells. They have different names that are there. Who cares? We're just gonna. They're in shells. I don't care how they load. And they also have. I don't know if I have it mentioned here, but they have. Some of them have different spins that they do. Who cares? Valence electrons. That's all we need to know. Okay. You need to know that they have subshells, or no? No. How's that? Easy? So we need to know that they correspond to rows. Well, no, that bottom one I do want you to know. That bottom bullet point. The number of shells corresponds to the number of rows. So if I look at my elements here, potassium is in the fourth row, which means that there's four shells that are there being filled. Different ways that we can represent the electron configuration that's dealing with shells, subshells, and electrons. For example, magnesium, you can say it's 1s2, 2s2, 2p6, 3s2, or not. You can just use the Lewis dot diagram, which just shows the valence electrons. Since that's all we're concerning with, that's a perfectly welcome way of doing it. Magnesium has 2 electrons that it can play with in its valence shell. You have 2 valence electrons in its outermost shell. There, I said it the way I wanted to. So hydrogen will only have 1, beryllium has 2, nitrogen, these 2 are actually, has 5, helium has 2, sulfur has 16 electrons, 2 in the first shell, 8 in the second shell, 6 valence electrons that would be placed in that shape there. So let's hold that for a second. Let's come back and visit it again. We talked about groups being one way to look at it, basing on chemical properties. Well, what is involved in chemical properties is the electrons. So ones that have similar numbers of electrons are going to have similar chemical properties. And there's 3 main groups that we talk about. The representative or main group, novel, which includes the noble gases. I'll tell you what that is in a second. The second is the the transition elements. And then finally, the intertransition elements, also known as the rare metals. You can see the color coding they have here tells us what the different ones are. Okay? So these would be the transitional ones, and these are what are the rare earth or intertransitional. And they basically fit in this part right here where this is located. Yeah.
Did you say that the representative or main group elements
yes.
are called something else too?
We break them down further too, yes. Okay. These are based upon the number of columns you have. Now here's what I want you to do if you have yours, is we're going to skip the the transition element. So if I make this, let me change the color. 1, 2, 3, 4, 5, 6, 7, 8. I basically have skipped this middle part. This tells us how many electrons are in the outermost shell, how many valence electrons they have to play with. So in this case, hydrogen, lithium, sodium, potassium, and the rest all have one electron. All have one valence electron. The ones in column 2 have 2. The ones over here in column 13, at least on mine it says 13, have 3, 4, 5, 6, 7. And we'll find that these guys in the very end, they have 8 in their outermost shell. They're happy. They're called the noble gases. Helium, neon, argon, krypton, xenon, radon. You notice in this table too, they also have these guys down here in the bottom. 112, 113. These are ones where we know they exist, we just don't know what the heck they're called. Like this guy here. He's unknown. These have been named, but they haven't. They only are present in nature for such a brief amount of time that they really have no function. Do you have a question?
You said the rows, how many shells they had filled?
How many shells that can be filled are determined by the rows. The number of valence electrons are determined by the columns. Interestingly enough, because they have the same number of valence electrons, they have the same chemical properties. And they can often substitute for each other. So for instance, potassium and sodium both have one valence electron. They both have the ability to combine with chloride. So I could have sodium chloride, table salt, or potassium chloride, which is also a salt substitute that you might see. And that's what we talked about, the valence electrons. It gets a little bit more screwy when you get into the intertransition and the transition elements. They don't quite fill in a regular pattern like they do in the other columns. The other way that we can classify them is based on their physical properties. And as this shows, where the red circle is, there's some that are metals, there's some that are nonmetals. The metals that specifically we're going to look at are the ones that are on the left-hand side. One in the column 1 and column 2. The nonmetals are the ones that are on the right side, okay, including the noble gases. And then there's some that are kind of in between, what we're going to call semi-metals or metalloids. Not that you need to, I'm never going to ask you, what do nonmetals look like? No. Alkali metals are basically the ones that are in the first column, and the second column is the alkaline earth metals. And as the name implies, they're very reactive with water, and they're almost never found in a pure state. The halogens, those in group 7, chlorine, fluorine, bromine, have a natural tendency to want to match up with those in 1A. So the people in the first column and the people in the 7th column often interact. The noble gases, again, the ones with 8 valence electrons, they're inert. The only people they combine with is each other. So helium would combine with another helium molecule. But helium doesn't have the ability to, has no need to mix with the rabble that is not in the rest of the periodic table. They're the noble gases. And then those transition ones we set in the middle, they're smaller in nature. We're not going to worry that much about them. That's those there. And then the intertransition are the ones on the 2 rows that are basically always pulled out of the periodic table. And I don't care that you know that there's a lanthanide and an actinide series. The interesting thing about the intertransition metals are they are also called the rare earth metals, and those are the ones that are have a very limited availability, and interestingly enough, they're the ones that are used in a lot of electronics, especially things like mobile phones, and there's only limited places that they're available. One of the big producers of these is China. So it's very interesting from a geopolitical standpoint. And why these are funky is that they got all kind of, they don't follow the normal electron filling process. That's about all you need to know about the intertransition metals. Stop the insanity. I agree. So we can group them by the number of electrons, and we can group them, and that's the groups, the main transition and intertransition, and we can group them by classes, basically how they interact with each other. Metals, nonmetals, and something called semi-metals. Taking a look at the ones in the first two columns, the alkali metals, probably the most important thing that you would need to know from these is that they conduct electricity and heat very well. So they're used as conducting agents. They readily combine with other metals. So they combine with each other. They also prefer to combine with nonmetals over on the opposite side. So like I said, sodium chloride, potassium chloride. And sometimes they're just found in the free state, as we have with gold, silver, copper, and platinum. Nonmetals on the right side of the table, the guys in the green there and the blue noble gases, what you need to know with these guys is that they're poor conductors of electricity, with the exception of carbon. And as I said, they combine with metals. They'll also combine with themselves, other nonmetals. There's some of them that are found free in nature. Oxygen, nitrogen, and carbon are the most specific ones. And we said the noble gases don't play with anybody. And then there's these weird group of folks called the semi-metals, and that's basically those that are on this jig-jag line here. They're poor conductors, and that's why we call them semiconductors, and these are the ones that are used often when low voltage is needed to be transmitted in a lot of electrodes, and again in a lot of electrical devices. So when we talk about a computer is primarily the chip is made of silicon. Silicon's right in the center of that semi-metal level. Okay. So they're kind of in between the metals and the non-metals.
This might be silly.
No, that's fine, because I'm probably selling one. Huh?
Light green and blue?
It's right along the ones that are on that border.
On both sides of the border?
On either side of it, yes. So I always say look for silicon, and if it's in that jig-jag there, it's probably a semi-metal. So these here. And they're not all, but predominantly they are. What do I want you to know here? Nothing. We'll cover it someplace else. Blah, 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 blah. Don't worry about it. Valence electrons, all I want you to know about. These electrons are the ones that are either gained, lost, or shared when we talk about the bonding of elements to form compounds. They're also the ones that are utilized for chemical reactions, and that's where we're going to focus on them. Whenever those valence electrons are lost, in other words, sodium gives up one, gained, chloride grabs one, or shared, as we'll see in the case of oxygen, they form a molecule, and that molecule can either be two of the same atom, so two oxygens joined together, or they're two different compounds, or two different atoms that form a compound, like water, sodium chloride. And what ends up happening here, if you think about oxygen, how many electrons does oxygen have? I'm sorry? 6, yeah. Let me rephrase that. How many valence electrons does oxygen have? 6. It's more than 6 electrons. So what they do is they share 2. And they double dip. The goal is to get 8 in your outermost shell. 8 valence electrons in play, and we're happy. So oxygen now has 1, 2, 3, 4, 5, 6, 7, 8. And this other oxygen has 1, 2, 3, 4, 5, 6, 7, 8. We're both happy. Okay. In the case of water, they also share an electron. And that's how it gets to 8 also. Hydrogen and helium are a little bit weird. Hydrogen's happy with 2. That's what they end up joining up like. The metals, the ones on the left side, are electron donors. Instead of, if we take, for instance, sodium, sodium has 1 valence electron, and rather than trying to find 7 others to join up with, which would be kind of ridiculous, it says, hey, you know what? Just take my 1 electron. I'll give it up. In the process, because he lost an electron, he becomes positive. He no longer is neutral, not same number of protons and electrons. He has 1 less electron that he had as a pure form, and we now call him sodium ion, and that is represented as a cation, where the T in cat should tell you it's positive. The ones on the right side, the nonmetals, their shells are almost full. They usually have somewhere between 6 or 7 electrons in the outermost shell. So they end up taking those electrons from sodium, and they now have more electrons than they do protons, so they become a negative ion or an anion, N for negative. And the only exception is helium and the other noble gases that have either 2 in the case of helium or 8 in the case of the other ones, and they're happy. We call that inert. They don't interact with anybody else. Semimetals, they're on the fence. They swing either way. I probably said it wrong, but oh well. They can either gain or lose electrons depending upon the situation. So they can end up becoming net positive or net negative. When we were talking about this neutrality, we're talking about the fact in the pure state, all elements have the same number of protons and electrons. Except for the noble gases, though, they don't like being that way. They would rather have their outside shells full in some process, and they will do what they can to lose electrons or gain electrons to get there. So, aside from the noble gases, pretty much all the elements, not pretty much, all the elements are neutral in nature, but they're unstable. They're unstable because they want to do something to get rid of or gain electrons to get to the outermost shell being full. Am I good with that? Those of you who've taken chemistry before, am I dumbing it down too much? Too much? Your colleagues are going to say, shut up. So oxygen needs 8 electrons in this outermost shell to be stable. It's in the second row, so there's 2 shells. Atomic number tells me that there's 8 electrons, 8 protons. The column indicates the number of electrons in its outermost shell, 6. And then what it needs to do is look for 2 more. You can either do it by bonding with another oxygen molecule and sharing as I showed, or they can go ahead and take those 6 electrons in the outermost shell and bond with something like hydrogen, 2 hydrogen molecules, 2 hydrogen atoms to form water. That's what I just said. There you go. All right. I'm going to stop